Electric motors are literally everywhere, from a super fast EV to the industrial robots that build them. But what if I told you that for decades, we've basically been running these motors with the brakes on? Yeah, there's a fundamental physical limit, a speed ceiling, that's imposed not by the motor itself, but by the electronics that drive it. Well, today, we're diving into a thesis that presents a genuine breakthrough, a new kind of inverter that just smashes that ceiling, unlocking a whole new level of performance. Okay, so here's our game plan. First, we're going to get to know the workhorse of the modern era, the electric motor. Then, we'll unpack the really clever ways we control it and figure out exactly where that speed limit comes from. And then, for the main event, we'll reveal the breakthrough inverter and look at the hard data that proves it can shatter those old limits. So at the very heart of all this is a specific type of motor that's really become the gold standard for any high-performance application you can think of. We're talking about the permanent magnet synchronous motor, or PMSM for short. These are the engines driving the whole EV revolution and countless other advanced machines. And it's all because of their incredible efficiency and power density. I mean, they pack a massive punch for their size. So what makes them so special? Well, instead of using a bunch of electricity to create the magnetic field in the spinning part, the rotor, they use really powerful permanent magnets. And that simple change cuts down on a ton of energy loss, which makes them super efficient and incredibly responsive. Now check this out. This slide shows the two main ways you can build these rotors. The one on the left has magnets just mounted on the surface. But look at the right. The magnets are embedded inside the rotor. This is called an interior permanent magnet, or IPM design, and it's mechanically way stronger, which makes it absolutely perfect for the high-speed challenges we're about to tackle. Okay, so we've got this awesome motor, but how do we actually tell it what to do? You know, controlling the three-phase alternating current that drives it is insanely complex, so engineers came up with a bit of mathematical genius to make the whole problem way simpler. And this trick is called Park's transformation. What it does, essentially, is it changes your point of view. So instead of trying to juggle three rapidly oscillating AC sine waves from the outside, it puts you in a reference frame that's spinning right along with the motor's magnetic field. And this is a fantastic way to picture it. From this new rotating DQ perspective, those crazy AC waves suddenly look like two simple, steady DC values. It's amazing. One value, we call Q, controls torque, that's the twisting force, and the other, D, controls the magnetic flux. And just like that, the control problem just got 1,000 times easier to solve. Now, with this DQ control, we basically use two different strategies. Think of them like gears. At low speeds, we use something called maximum torque per ampere, or MTPA. This gives us the most grunt for every amp of current, perfect for getting off the line. But to go really fast, we have to switch to a different mode, flux weakening. This sounds completely backward, right? To go faster, you intentionally have to weaken the motor's magnetic field. See, as the motor spins faster and faster, it generates its own voltage that pushes back against our power source. We call this back EMF. It's like a headwind. By using some of our current to create a countermagnetic field, we reduce that headwind, which lets the motor spin even faster. But even with this really clever flux weakening trick, you eventually hit a hard wall. And that limit isn't in the motor itself, it's in the inverter. That's the electronic box that turns DC battery power into the AC power the motor actually needs. This graph right here is absolutely key to understanding the problem. Think of it as the motor's operating map. The big circle represents the maximum current the system can handle. You go outside that, things start to melt. But that ellipse, that's different. It represents the maximum voltage the inverter can supply. And to run the motor, our operating point has to stay inside both of those shapes at all times. And here's the kicker. As the motor spins faster, that back EMF, that voltage pushing back at us, gets stronger. And to overcome it, the inverter needs more voltage, but it has a fixed supply from the battery. So what happens? As speed increases, that voltage limiting ellipse shrinks, and it shrinks fast. Our operating window gets smaller and smaller until, poof, there's no overlap. We're completely out of room. You've just hit the inverter's speed limit. So the big question is, how do you break through that voltage wall? Well, the answer this thesis presents is to just stop accepting the voltage limit as a given. And that's where this amazing piece of hardware comes in, the Z-source inverter. At first glance, it kind of looks like a standard inverter, but look closer at that unique X-shaped network of inductors and capacitors right at the front. That Z-network, as it's called, is the secret sauce. It's what gives this inverter a superpower that traditional inverters have never, ever had: the ability to boost its own voltage. The best way to think about it is like a turbocharger for your motor drive. The Z-source inverter, or ZSI, combines a traditional inverter and a DC to DC boost converter into one elegant, efficient package. It gives you an on-demand voltage boost precisely when you need it most, when you're at high speeds. And it does this using a trick that would literally make a normal inverter explode. It's called a shoot-through. For just a tiny fraction of a second, it intentionally creates a short circuit. This lets energy get stored up in those inductors in the Z network. Then, when that short circuit is released, the inductors discharge all that stored energy, adding it on top of the source voltage and creating a massive boosted output for the motor. It's genius. All right, so we have the hardware that can smash through the voltage ceiling. Now let's see how this research pairs that power with a brand new control algorithm to completely redefine the limits of motor speed. Now, this diagram might look a little complicated, but the real magic is happening in that new section labeled Part C. That's the boosted voltage flux weakening, or BVFW regulator. Think of this as the new brain of the entire system. While the motor is spinning at high speed, this block is constantly calculating the exact voltage it needs and telling the ZSI precisely how much to boost the power to keep everything running perfectly. And what's the result of all this? Well, instead of the motor's power just dropping off a cliff once it hits its base speed, this integrated system lets it maintain constant power. And that means more performance, more speed, and a much, much wider operating range. And here is the proof, right from the simulation data. Check out the D and Q currents. Everything's running along smoothly until about the 0.7-second mark. That's the moment the motor hits its old base speed. You see the BVFW controller kick in, driving that D current negative to weaken the flux. This is the system in real time actively fighting back against that back EMF to push past the normal speed barrier. And the numbers? Well, they speak for themselves. The simulation shows the motor's natural speed limit is just under 1,100 electrical radians per second. But with the Z-source inverter and the new control strategy, it achieves over 1,350. That is a performance increase of more than 23%. It's just pushing far, far beyond what was ever possible with that old voltage limit. So let's just recap the whole journey here. We start with a really robust interior PM motor. We figure out that the traditional inverter creates this voltage ceiling that chokes its top speed. We then introduce the Z-source inverter to act like a turbocharger, smashing that ceiling. And finally, we use a new, intelligent algorithm to control that boost, unlocking a whole new world of high-speed, constant power performance. You know, this research does a lot more than just make a motor spin faster. It fundamentally changes a limitation that has held back electric drive design for decades. And it forces us to ask a really exciting question. If that voltage limit is no longer the hard wall it used to be, what other applications can be completely revolutionized? What new frontiers in robotics, in transportation, in industry are now wide open for us to explore?